Welcome back to ECE 442-542. We are fast approaching exam number 3, which is which will occur next Wednesday, not this Wednesday, but next, on the 15th of April. And between now and then, you have 2 homework assignments, and that's really sort of the content of exam number 3. Homework 5 is due this evening. Homework 6 is due in a week at the same time, not the same day. We are scheduled for another review session, and I believe that one is back in the same location that we had our first review session. We're just making sure that you're paying attention, or that I am. I need to double check that, but I'm pretty sure that's where review session number 3 is, or will be. Exam number 3 material should be on D2L, and your 542 project is due on the last day of class, on the 6th of May. That sounds like a long time away, but I believe it's going to be here before we know it. Today what I want to do is get into new material. We're going to assume we've concluded the design approach by Ragazzini. Now we will start PID controllers, and we'll do that by also introducing root locus sketching strategies. And the first part of that will be to look at proportional control. What can we do with just a gain as our controller? How can we adjust the closed loop poles based on just adjusting a gain? And think of a knob. You're simply turning that knob from 0 all the way to infinity, and you're trying to determine how does that gain impact or influence your closed loop pole locations. That's really the whole idea behind the root locus. And we will see that 1 plus k g of s is our denominator polynomial, or that governs the behavior or the closed loop poles of our system, where we will be adjusting k from 0 to infinity, and that's really the definition of the root locus. If you view 1 plus k g of z equal to 0 as a complex equation, or an equation that has complex roots for z, you can satisfy, or you can say kg of z is equal to -1. -1 you can view as a complex number having a magnitude of 1 and an angle of -180 degrees. Those two conditions, the magnitude condition and the phase angle condition, are what you use to derive all of the root loci construction techniques. And if you understand how these roots move around in the complex z-plane, that's a powerful strategy for designing controllers. And we will try to illustrate that or show what you can do, but the rules, if you've already taken an earlier class in automatic control, the rules for constructing the root loci are the same. It's just now they're in the z-plane, meaning the region for stability is now the unit circle and not the entire left half complex S-plane. It's now this unit disk in the z-plane. But if you have a constellation or a collection of poles and zeros, sketching the root locus associated with those poles and zeros is the same as what you've seen if you've already had an earlier controls class. If you haven't, we'll try to learn those as we go. And if you need material, Chapter 13 deals with the construction of the root loci. Chapter 14 talks about a design using the root loci. Those are in Sham's outline, those particular chapters. And you can go to that to gain more familiarity with that material. Let's get started by getting a conceptual picture of this PID controller approach. And you can think of it in this block diagram form. You really have 3 pieces to this controller. You have a proportional piece, which simply takes the air signal and scales that air to create part of or a component part of the input U into the system. There is an integral piece that integrates the air signal and scales that integrated air to produce another piece of the total input to the system, U. U is made up of three different parts: a proportional part, an integral part, and a derivative part. The derivative part takes the derivative of that air signal. That gives you a way of really sort of forecasting or inferring where you're headed based on the derivative, the time rate of change of the air. You can sort of say, oh, my air is sloping at this magnitude or at this value. Now, if I sort of just assume that I'm continuing in that direction, the derivative is sort of an anticipatory component of your controller. The proportional piece just scales the present air signal, so that's sort of here and now. The integral piece is integrating that air from minus infinity all the way up until now. That's sort of dealing with the past behavior of the air. These three pieces then all have a different flavor. I'm just using a continuous time or the continuous time waveforms to illustrate what these three pieces look like. The PID, you probably, if you're in an interview, you probably don't want to say, oh yes, we designed PID controllers. That might not go over well. You might want to just say, oh, we are learning PID controllers. That's just an abbreviation for proportional integral derivative controllers. Say PID, they'll say, where are you getting your control education? Just saying. So you might want to refer to it as PID, proportional integral derivative. This is really what I just said. You have three pieces to that controller, and they all three are doing a little slightly different function in that controller. You could visualize what they are doing in this plot. Let's assume that you've designed your controller to reduce the air. I have now drawn a air trajectory, and I've simply arbitrarily located now as t sub 0. Now is what the proportional controller is looking at. It's looking at that particular E of t0 and responding by making a part of your control signal proportional to the present air. The integral is looking at what the air was before now, and it's integrated all of that air information up and from minus infinity all the way up to the current time t. That's the integral piece. The derivative piece is, you can calculate the derivative of the air at the present time, and that sort of tells you in what direction you are headed. That anticipates where you're going. So if you want to change the dynamic behavior, you're probably thinking about this derivative piece. If you want to reduce the steady state error or improve your steady state accuracy, you're probably playing with the integral piece, or need to include the integral piece. You can have a PID controller that just has one piece in it. Maybe you want a purely proportional controller. You just have a P. You set your K sub I and your K sub D gains to 0. You have a proportional control. We will get into, before the second exam, a PI controller. Not a private investigator, but a proportional integral controller, where the derivative term has been set to 0, and a PI controller is usually selected to reduce or improve steady state accuracy. It may slow down the system a little bit, but you're really worrying about your steady state error with a PI controller. If you're trying to change the transient behavior after you've reduce the steady state error, maybe you put in a derivative piece, and now you use all three terms. You have a PID controller. You can sort of do this in stages. You can say, oh, I want the PI piece to give me 0 steady state error, and I want the derivative piece to try to help me with my transient behavior. The PID controller can do a lot for you in terms of changing the behavior of your dynamic system. Let's start with the basics. Let's just start this PID controller discussion by looking at the very first piece where we simply say, suppose that our controller is purely proportional. Yes? So the question is, will you ever have a PD controller, or will you ever have a ID, an ID controller? I haven't really seen an ID controller, but I have seen a PD controller. We will probably, and that's a proportional derivative. Maybe you're not so worried about the integral part or the steady state accuracy, but you're more interested in the transient behavior. So you might have a PD controller, and in this class we will probably always just assume these ideal scenarios, but a PD controller in the ideal case has a pure derivative, and you really don't want to be doing that. If your error is any bit noisy, now you're differentiating this really messy signal, and you're making it even worse by differentiating it. But in the real case, in the practical case, you would put a pole out at a higher frequency that would roll off the gain, or at least not make it continue up as your frequencies get larger. The gain you would want to at least keep flat and maybe ideally roll off at high frequencies. Yes, you can have other controllers besides the P, the PI, and the PID, but those are the three that we will focus on in this class. You could have a PD controller. To start, like I said, let's just look at what we can do by adjusting this gain K. And in all three of these, if we did go back to the PID controller, just think about this like having three different knobs. You have a case of P knob, a case of I knob, and a case of D knob, and you can adjust those. We'll just keep them non-negative from 0 up to infinity. Those three knobs can be independently adjusted. To begin with, we're going to stick the case of I knob on 0. We're going to lock it at 0. We're going to lock the case of D knob at 0, and we're just going to play with the case of P knob, the proportional gain in this controller. And that's what I'm trying to suggest here. Now our controller is just a gain. And I've just called it K. Maybe I should have called it case of P, but now I'm just calling it K. I got tired of writing subscripts. But this is now a proportional controller. You can compute the closed-loop transfer function between the reference signal R and the output Y. That's our cheer, Kg over 1 plus Kg, because we have unity output feedback. Whoops. Negative output feedback, just making sure I'm awake. Did everyone catch that? If you didn't see it in the diagram, it was implied in the denominator of the closed-loop transfer function. I was assuming that if I have 1 plus Kg of S. If you went through the block diagram algebra, you would have said, Dr. Tharp, is there supposed to be a negative sign on that feedback because of your transfer function expression? Oh, yes. You could verify it. That's what you need to be getting good at doing now, is convincing yourself of all of these different pieces and ways of checking. And I think I'm starting to make you a little bit nervous, some of you maybe, because I'm maybe under-specifying things in the homework. Maybe I just give you one design spec and I say, give me a controller. It's theta sub d. You didn't tell us. You didn't give us an overshoot, percent overshoot. You didn't give us a peak time. Now is when you earn your wages. This is why you're taking this class, so you get a little bit more comfortable with making these judgments. What's a nice zeta value? If I had to tell you, we have a competition, and walking in front of you are these different zeta values, which zeta would you pick? Zeta equal to 1. Here's zeta equal to 0. And zeta's all in between. I apologize for those that are listening. You don't get the visual. But now you know, if you watch this again, you can see the visual of what zeta equals 0 and zeta equal 1 and all in between, right? You have an infinite number of zetas. What's a nice zeta value? 0.707. Isn't that sweet? That's a pretty good zeta value. That corresponds to a 5% overshoot. It's a nice trade-off between speed of response and overshoot. It's not a lot of overshoot, but it helps you get to where you're going quicker than, let's say, a zeta equal 1. But if I haven't specified, pick zeta, I wouldn't pick it equal to 0, but you could pick zeta between 0.5 and 1 without a problem, probably. And you can just say, I'm going to select zeta if you need to pick that to find your theta sub d. Is that clear? Sort of got on a tangent, but you're going to be needing to pick zeta values or closed loop pole locations. That's actually why I kind of like to start with the Ragazzini approach, because now that forces you into what poles should I pick for T sub C of Z. Now you are going to start looking at ways of doing that for particular systems. Let's start with an example. Sometimes it's easier to just think in terms of examples. Suppose we have a system that's given by g of z equal to 1 over z minus 2, and again we're assuming c of z is equal to k. What is t sub c of z? And I think, yes, I put the negative sign, so it's unity, negative unity output feedback, and we have kg of z, our cheer, over 1 plus kg of z. And if we plug in our g of z, and if we get a common denominator in the denominator and cancel the two denominators in the numerator and denominator, we end up with k over z minus 2 plus k. Questions on that? That's now our closed loop transfer function based on a proportional controller. If I now ask you for the closed loop dynamics, what would you start seeing or thinking? What governs the closed loop dynamics? Are we comfortable with that description? Closed loop dynamics. What am I meaning? I've taken off my glasses so you could be doing all sorts of things and I wouldn't know. But I'm hoping you're thinking. Those wheels are turning. Closed loop dynamics. Are the closed loop dynamics anywhere on the screen? What's T sub C of Z? As a reminder, what is that? That's the closed loop transfer function. which contains the closed loop dynamics. The closed loop dynamics are where, or what governs the closed loop dynamics in general on this screen? One plus kg of z are governing those dynamics, and that's just this guy, isn't it? That governs the closed loop dynamics, 1 plus kg of z. Or you could think of it in another way. You could say, oh, I'm interested in the roots for my closed loop dynamics. Those are the roots of 1 plus k g of z equaling 0. The values of z that satisfy that are my poles in my closed loop system, and those govern my dynamics. And I'm looking at those for all different values of k, and in particular for k's between 0 and infinity. You could think of this another way. The roots of 1 plus kg of z, or what values of z allow that to be true, can also be found by looking at the numerator of 1 plus k g of z and setting that numerator equal to 0. And the numerator of 1 plus kg of z, this is now 1 plus kg of z, and I'm looking at the numerator of that, which is this. That's now this guy, and I'm going to set that equal to, so I now have z minus 2 plus k. Maybe I could have reduced my highlighter. I'm almost out of ink on the highlighter, so I'll reduce the ink there and say now this is equal to 0. And what I want to do, since that influences or governs my closed loop dynamics, I have total freedom over k. And I hope I can find some k's that will give me a good or an acceptable dynamic behavior. I can let k be between 0 and infinity. Some of those may be good choices, some of those may not be so good. And hopefully there's some good choices, but we want to now adjust k to locate the closed loop pole. I only have one since I have z to the first power. I only have one pole. Adjust k to locate the closed loop pole at an acceptable location. And we could actually look at, so now we have, if we solved that equation right here, then we have z is equal to 2 minus k. And we want to know what values of k can we live with or give us reasonable values. Actually look at this from a more visual perspective. If we now said, you know what, let's look at this in the z-plane. And I hope you will humor me by, you can virtually draw that circle, since I've given up on drawing circles. But you now have this unit circle. You want your closed loop pole to live in there by the appropriate choice of gain k. Where are we starting with our open loop pole? With k equal to 0, where is our pole? It's at z equal to 2, isn't it? We now actually have a pole right there in the open loop. There's our open loop pole. label that with is that in a good location? No. So we can't not control this system if we want it to be a stable system. If we didn't apply a controller, this system would be unstable. Does everybody see that? It's starting with it being unstable. We now want to adjust the dynamics by the choice of K. What's going to happen when I start increasing K and making it more positive? Are my roots going to be real or complex? Real, aren't they? I only have one root, and they're all going to be real if I keep K real. And I'm keeping K positive and making it real. Do you see that as I increase K, the closed loop poles could just travel along the real line from 2, a positive 2, all the way to minus infinity as I make K bigger and bigger. Is that clear? That's actually a root locus diagram. Hint, hint. We haven't gotten there yet, but you've now sketched a root locus diagram. That red line is your root locus, and we can say that this red line is now the locus of potential closed loop poles. Potential is important. Do we want to crank up the gain K such that we put a closed loop pole there? That's beyond the unit circle. We probably don't want to make K that big, do we? Do you see the sweet spot? The nice location or segment on the real line that you would like to have K be between, or that governs K? As you crank up this knob, K going from 0 up to infinity, you're going to reach a value where K reaches Z equal to 1. And that's going to be, if I that's going to be a value of K equal to 1. That's maybe unfortunate that it's equal to what Z is. But let's now look at one possibility, and I hope that you are clear that there's an infinite number of stabilizing values for K. Since there's an infinite number of gains between, or values of K between 1 and minus 1. Suppose now we look at one possibility. We know that our closed loop polynomial is given by Z minus 2 plus K. That was our closed loop polynomial that we set equal to 0. We have Z minus 2 plus K. This is our closed loop polynomial. And when we set it equal to 0, we have our closed loop equation for the closed loop poles. This is now our closed loop polynomial. We want to set that equal to some desired polynomial. And just for grins, let me say a desired polynomial is z minus 1/2. Which means that I desire my closed loop pole to be at 1/2. I want it to be far enough inside the unit circle, but not too far. So that's one possible value for a closed loop pole. And if I now have a desired polynomial set equal to my closed loop polynomial, where the closed loop polynomial has an adjustable gain k, that's the only unknown in that equation. I can solve that equation for k to determine what that needs to be. And I can do that by equating coefficients. And in particular, I'm interested in the constant coefficients, since the coefficients of z to the 1 are the same already. I don't have to worry about those. If I look at the constant coefficients, I then have on the left minus 2 plus k equaling minus 1/2. If I solve that for k, I get k is equal to 3/2. That's now a value of k. If I now plug that k value back into my closed loop transfer function expression, which was a function of k on the far right, I now have my closed loop transfer function. T sub c of z is now 3/2 z minus 1/2. Is that a stable closed loop system? Everybody, I hope, knows that if you set the denominator equal to 0 and find the value of z where that's true, that's now your closed loop pole, and you've located a closed loop pole at z equal to 1/2. And that's inside the unit circle. Our closed loop system for this choice of gain k is indeed stable. What's our controller? Let's just remember what we were assuming. We were assuming a proportional controller, and we found what k was equal to. That's now our controller. Controller, c of z, is just k, which we've picked a particular value to place our desired polynomial at z minus 1/2. This is now a proportional controller. And is that giving us a well-behaved closed loop system? By that, did we cancel any unstable poles and zeros in our system? Was our system stable to begin with? Was our open loop system stable? No, because it had a pole outside the unit circle. It had a pole at z equal to 2. Did we have to cancel that unstable pole to stabilize the system? No. And do you ever want to cancel unstable poles or unstable zeros? Not unless you want to lose more points than your exam is worth, right? That's the only reason you would do that. And we're beyond April Fools. So don't do that. Do not cancel unstable poles or zeros with your controller. Now you can have unstable poles in your controller. You might have an unstable system that you have to stabilize with an unstable controller. Yes? So I can try to explain that. That was in an earlier lecture, But if you cancel an unstable pole or an unstable zero with your controller, that's going to produce an internal instability. That's the cleanest way to maybe say that. Meaning you might have now an unbounded air signal between your reference and the air. That's a part. So you have these different transfer functions in your closed loop system, wherever my block diagram ended up. And now if you did, here we didn't have that, but if you did cancel an unstable pole or zero with your controller, you're going to have an internal instability. It may look fine between R and Y, but between R and E, or between R and U, or not shown here, but between the disturbance D and the output Y, one of those might be bad. And that's not what you want. So you might think that, oh, look at this system, it's beautiful between R and Y. You plug it in or you energize it, and after a little while it's burned up and not working anymore, or it's been chattering and you've broken something because an internal signal has gone unbounded because you tried to cancel an unstable pole or zero with your controller. Does that answer your question? So you should sit back, and that's in some earlier lecture I tried to talk about that, but just know that you can't do that. We learned that from the Ragazzini approach, but you can't do it any time. Okay? But you can have an unstable controller. You could plop a pole outside the unit circle, and that might benefit you. You just don't want that pole to cancel an unstable zero, or you don't want to cancel an unstable pole with an unstable zero. That's what you want to avoid. You can put poles and zeros outside the unit circle. In earlier classes, I talk about having a pole shaker and a zero shaker, and you're now sprinkling those poles and zeros on your complex Z-plane to give you the behavior that you want. Just like you season your food, you get it just right with the seasoning. You want to design your controller with the appropriate poles and zeros to get that just right. And what do we mean by just right? It has the appropriate transient behavior and steady state accuracy. That's what just right means in this class. And that may mean that you have unstable poles and zeros in your controller. They're just not canceling things outside the unit circle. You can cancel poles and zeros inside the unit circle, but I wouldn't do it if they're real close to the unit circle. I would avoid canceling things that are even very close to the unit circle. Does that help with that? But you can have an unstable controller. Now I have to remember where I was. Oh, so I wanted to make that point. Let me write it down. This controller, for a proportional controller, had no cancellations of unstable poles or unstable zeros with C of Z equal to 3/2. We cranked up the gain to try to, what? Push that unstable pole inside the unit circle. We had to crank it up, but we didn't cancel anything. We just increased the gain. We probably don't want to increase the gain too much, though, do we? Now, what else might we be interested in? We've stabilized the system. We start celebrating. Not so fast. maybe. What's the DC gain? And why am I even asking about the DC gain of our desired or of our closed loop system? Why am I interested in the DC gain other than, oh, it's a question on the exam? Beyond that, what use is the DC gain of your desired transfer function? What does that give you? What does that tell you? Can we calculate it first, and then we'll figure out what it does for us or not? How do I find the DC gain of T sub C of Z? That you should just be able to do in your sleep, right? You compute this, or you evaluate that transfer function with Z equal to 1. And what does that give you? Well, the numerator didn't have a Z in it. That was 3/2. The denominator was first order. We replaced the only Z downstairs with 1. We get 1 minus 1/2. We now have 3/2 divided by 1/2, or a DC gain of 3. So, does that tell you anything? You need to be developing some insight into what this means, is why I'm going through this. What does this actually mean? You now have a DC gain of 3. What if I said, okay, what's the steady state error to a unit step? Does that even make sense to you? Are you interested? What if you applied a constant of 1 to this system? What would happen? The output goes to 3. How does it go to 3? Really fast? Or does it just instantly go to 3? Does it smoothly go to 3? How does this go to 3? Can you tell me? Can you sketch? If you had an interview and the interviewer, she goes, what's the output response of this system? Hopefully you don't get too choked up, but you can take a breath. You can just think about what's going on. What do you know? You know it's going to 3, don't you? What do you know? Well, what is the reference signal at time infinity? 1, because it's a unit step. So you just start talking, you start writing this on the napkin. And as you're thinking, you're trying to process. And you've just told me that the output Y, the DC gain is 3, the input is 1. That's going to produce your steady state output of 3. But the error signal, if you go back up to your block diagram, you might just start sketching a block diagram. Buy yourself some time. You say, okay, here's my block diagram, here's my system, G of Z, here's my controller K, my error signal, error is R minus Y. You now know that you can say, okay, R of infinity minus Y of infinity is 1 minus 3, or my steady state error is minus 2. What does that look like in terms of a sketch? I shouldn't put it in T. This is N, but I'm going to probably just sketch it as if it was a continuous waveform. What does this look like? Where did I want to go? Maybe. Maybe you wanted to go to 1. This is R. Where did you go? You went to 3, so that now your error is right there. How did you get there? What's the curve look like? What's the order of your system? First order. Does that tell you anything? When I say first order system, what are you thinking about as an electrical and computer engineer? Maybe. You have one energy storage device, don't you? An energy storage device might be a capacitor, might be an inductor. You have an RC circuit. What's an RC circuit do for you? You charge up that capacitor, don't you? And what's the curve look like? Does it ring? Does it oscillate? Does it go up and down? No, it just gradually goes to its steady state. It's smooth, isn't it? It's starting here at 0 and going to 3. Is that making sense? How quickly does it get there? 5 tau. 5 tau is infinite, isn't it? Or roughly. And you can figure that out based on R. Your R value is 1/2. Your radius is 1/2 for this system. And if you needed to label that curve, you could based on the radius of your system. Now, are we happy with this, or is your boss happy with this after you designed a controller? You go in, you go, I stabilized your unstable system. And they go, oh, let's see what it looks like. You inject 1 and it goes to 3. But it's stable. Sure. But I've hired you to solve my problems, not to, well, that may be solving the problem. Maybe that's what you want. Maybe you wanted a DC gain of 3. Maybe not. Therefore, we may need a different controller structure. Right? So the controller structure is, what's our controller structure? An open door? What were we assuming? Just a gain, a proportional controller. Maybe that's not what we need. Maybe we need a PI controller. That's what I mean by a different controller structure. A PI controller will give us more parameters to adjust, and it might be able to reduce that steady state error. Is that clear? That's what I'm meaning by we may need a different controller structure if you're not happy with that. This proportional control may not produce an acceptable steady state error. Is that clear? So if you're not happy with that accuracy, steady state accuracy, you might say, oh, maybe I'll make my controller a little bit more complicated. I'll put an integrator in it instead of just a gain. So now I have a gain term and an integral term, and that integral term is good for reducing steady-state error. That's why we might use it. How many stable solutions do we have for this system? How many ways can you find a stabilizing gain value, K, for this system? How many are there? There's an infinite number. What if we increased K? We know that we may be sacrificing steady-state accuracy, but we can stabilize this system with all sorts of gains, can't we? What if one could increase K to yield a deadbeat response? I might ask that on the exam. I might say, design a controller, a proportional controller, to give you a deadbeat response. And I won't have 85 different answers. I should just have, well, I might have 85, I hope not. But I would like to think I have 85 correct answers. All the same with this question. Now what am I doing? Has my closed loop polynomial changed? If I have the same system, I haven't changed anything. I'm still using a proportional controller. My closed loop polynomial is still z minus 2 plus k. I have z minus 2 plus k, and if I want a deadbeat response, what do I want to set that equal to? Let me emphasize the deadbeat nature, and I'll just say minus 0. This is, I want a desired pole at the origin. And if we now equate coefficients, and in particular the constants, we have minus 2 plus k equaling 0, or k is now equal to 2. What's the closed loop transfer function now for that choice of controller? C of z is now equal to 2. What's t sub c, capital T sub c of z? You just scroll back and you say, well, I derived the equation. That was k over z minus 2 plus k. Plug in k equal to 2, and you end up with 2 over z. And that's now a closed loop. Is it stable? Does it give you the deadbeat response? You need everything in your denominator to be z's, right? And you just have a first order system. You have z to the 1, no constants in the denominator. This is what you want. We found c equal to 3/2 was okay for whatever reason. It stabilized our system. C equal to 2 was okay. It gave us a deadbeat response. Now let's look at all the different possibilities. Is there a limiting value of k for stability? And here I like to sketch this on a napkin, meaning I like to see what's going on. We have 1 and minus 1. We have an open loop pole at 2. And we know as we adjust the gain k from 0 all the way up to infinity, we can map out closed loop poles from 2 all the way to minus infinity. But, so this is now our root locus. That's the locus of closed loop roots of our closed loop transfer function, denominator roots, as k goes from 0 to infinity. Can we identify points on that root locus that determine the boundaries of stability? Is it clear? Whoops. Maybe we're not stable. Was that stable? Only for certain values of k, right? What k's do I want? Where's the lower bound on stability? That's when we crank up the gain k to get to that triangle. This, I would say, is now our lower limit on stability. What's the upper limit? It's now when we crank up the gain to get to that square. This is now our upper limit. And we can calculate those two values of gain k. The lower, which is the triangle, is z minus 2 plus k equal to z minus 1. Or k is now minus 1 plus 2, or 1, and we knew that already. We had to get the gain bigger than 1 to become stable. The upper value of gain k is when z minus 2 plus k is equal to z plus 1. This is now k is equal to 1 plus 2, or 3. And those are our two limiting values on stability for our proportional controller. Therefore, k between those two limits is what we would like to do for stability. Is that clear? That knob now better not be outside of that range if you want a closed loop system that's stable. It needs to be bigger than 1 and less than 3. And we've really just shown a root locus diagram for a very simple system. A standard root locus is given by the roots of 1 plus k g of z equaling 0 as k is increased from 0 up to infinity. And what could you do? You could manually determine this set of values z that satisfy that equation for different values of gain k between 0 and infinity. You could plug in k equal 0.1 and find the values of z that satisfy that. You now have a 10th order equation or 10th order system. You now have 10 roots. That's where your roots would be for k equal to 0.1. You make k equal to a half. Calculate the 10 roots. k equal to 1. You calculate the 10 roots, and you see this pattern of closed loop poles being sketched across your z-plane as k varies from 0 to infinity. Let's look at another system that might give us a slightly different pattern than one that's just on the real line. Suppose we now say, here's example 2. Again, let's assume we have a proportional controller, but our system now, g of z, is, let's say, 1z times z minus 3 halves. And now what we want to ask is there a stabilizing value or a range of stabilizing values in our proportional controller, K? Again, maybe this is in an interview, and what have you learned to do? Buy yourself time. To give yourself time to think. So you now start saying, oh, you wanted to know about the closed loop stability of this system. I'm assuming you were interested in the standard unity negative feedback configuration. There's your proportional gain. You now have your plant, which had, what's the order of your plant now? It was second order. Was it open loop stable? Where are your open loop poles? 0 and 3 halves. Are you open loop stable? No, because one of those is outside the unit circle. But now what is your transfer function between the reference input and the output? This structure is not unlike what we've just looked at. That's our cheer, kg over 1 plus kg. We want to know for stability what is the range of k for all roots of 1 plus k g of z equal to 0 to lie inside the unit circle. Meaning, as this pattern of poles is moving around in the z-plane, and there are particular patterns for this, you have to find a range of k where they're all simultaneously inside the unit circle. If you can't do that, you can't stabilize the system with a proportional controller. If just one is remaining outside the unit circle, that's all it takes to be unstable. You have to have all of your poles, and in this case you have 2 of those if you don't have any more complicated controller than a proportional controller. You need all of those poles simultaneously to be inside the unit circle for a range of gain k in order for the system to be stable. So let's now look at what we have, and all of this is influenced by that expression. Everything that we do now, as we're adjusting k, is determined by 1 plus k g of z equal to 0. That's the denominator of our closed loop transfer function, and that's what governs the stability behavior of our system. Let's now look at, then, the root locus of g of z that results from this configuration. We have 1 plus k g of z equal to 0. And as I said before, this is an equation that could have possible complex values for z that would satisfy this equation. Now can solve that for kg, and we see that kg is equal to -1. But if we're dealing with complex numbers, we can write -1 as a magnitude of 1 and an angle of -180 degrees. It could have been plus 180, but I like to just stick with -180 degrees. It's the same point. Those values of z that satisfy a magnitude of 1 and have an angle of -180, those points, locus of points in the complex z-plane, are the root locus. That's the root locus. Now, we are going to restrict k to being non-negative. If k is greater than or equal to 0, what can you say about the angle of k g of z? If k is non-negative, how does that change the angle of kg of z? If I gave you, so just start thinking of an example. Say, oh, g of z is some transfer function. In our case, it was 1 over z times z minus 3/2. You could, given a particular z, compute the angle of that expression. If it's a complex number, how do you find the angle of a complex number? You just look at the imaginary part and the real part, and you take their ratio and you do an arctangent, right? K is positive or non-negative. How does that impact the angle of g of z? It doesn't, does it? So this is equivalent to just g of z, and that's equal to minus 180 degrees on the root locus. Meaning we now can find all of those points in the complex z-plane that have an angle of minus 180. Now, if I said sketch the pole zero pattern in the z-plane for our given choice of g of z, what would that look like? Again, I'm buying time. If somebody asked you to sketch the root locus, how could you at least get part of the points associated with that? You sketch the z-plane, and then you put on that the open loop poles and the open loop zeros. And that would start to get you some credit. Have any finite zeros in our g of z that this example is? No, we had no finite zeros, so we have no zeros. Do we have any x's? Poles, finite poles. Where was I? Yes, and those are at 0 and 3/2. We can now sketch a pole there and a pole at 3/2. Now, what I'm going to do is I'm going to put some hypothetical points on here and say, here I want to see, is that star, does it belong to our root locus? Does this square belong to the root locus? And I'm not very creative, but everything's in the cloud, so that's a cloud. So now you can say you learned about the cloud in digital control. Now I want to know, is the star and the cloud are sort of related, aren't they? Maybe that square should have been a sun or a moon, but it's a square. Which points, those three, which points, the star, the square, and the cloud, lie on the root locus? Because before, when we just had that single pole, half of the real line belonged on the root locus. Now, is it possible that any of these segments of the real line belong on the root locus? And last semester in the earlier class, when we started talking about root locus, came up with this French bread thing, didn't we? And we talked about this infinitely long French bread, which is the entire real line, and our poles and zeros actually cut that French bread up. If you wanted to think about that line segment as being a piece of French bread, you've now made two slices in it, one at the origin and one at 3/2. You now have three segments of French bread. Is that clear? You have a French bread piece from 3/2 all the way to plus infinity, a finite piece, I'd probably have gotten that one growing up, between 0 and 3/2, and then my bigger brother got the other infinitely long piece from the origin to minus infinity. Do you see these three line segments? We now need to determine which of those three, or all of them, on the root locus, 1, 2, or none. That's our question. We want to know which of these pieces of the real line are belonging to our root locus. And the way that we can do that is we can compute the angle of g of z at each of those points. And the angle of g of z is determined by the poles and the zeros and how they behave relative to those locations, the star, the square, and the cloud. If I ask you, what's the angle that I have to make to go from 3/2 to the star, what would you say? Do I have to look up or down? No, I'm looking straight across. What's that angle? 0. Everybody see that the angle from 3/2 to the star is 0? What's the angle from the origin to the star? That's also 0. And where are those angles? They were in the basement of our overall transfer function, so we would subtract those to get our net angle. We now have a numerator that was constant. That didn't give us an angle. Or an angle of 0. This system may not be stable. Sorry. It's going unbounded, isn't it? No. But we have 0 minus 0, the angle of 2 to 3/2, minus 0, the angle at the origin. What's the overall angle? At star, it's 0. And what was the angle supposed to be on the root locus? Minus 180. So that segment, that piece of the French bread is not on the root locus. What about the square? If I now am at 3/2 and I have to find the angle from 3/2 to the square, what's my angle? And the angle is always measured from the positive real line that's going off to the right from that singularity. I'm now at 3/2. I now need to look behind me. I now need to turn 180 degrees to get to the square. What about from the origin? What's the angle from the origin to the square? 0. So what's my net angle? I have 0 for the numerator. I subtract the angle due to 3/2. That's 180. So I now have minus 180. And I subtract 0. What's my net angle? Minus 180. Is the square segment on the root locus? Yes. So now I know that this piece belongs to the root locus. What about the angle to the cloud? I have to turn through 180 degrees. At 3/2, I turn through 180 degrees. I subtract those two, and what do I have? Minus 360. That's not minus 180, is it? The line segment from the origin all to minus infinity is not a part of the root locus. The only piece of the root locus is between 0 and 3/2. We will learn that this will have a branch going to the right. This will have a branch going to the left. They will meet, and they won't stick. They have to go somewhere, and they can't go anywhere else on the real line, so they now have to take off and go vertical. And if I'm worried about something being inside the unit circle, do you see that there's a lower bound on the gain k, and there's also an upper bound on the gain k before those two go outside the unit circle? I have a range of k for stability, and we'll have to figure that out on Wednesday. Is this making sense? Try to think through different pole zero patterns and their angles and how this French bread is or is not on the root locus.